Hello all. So today we will be discussing TIFR 2020 question paper, the problem number 30. So this problem it is practically, uh, let's say, a taunt to your group action understanding. Okay. So group action is basically defined from G cross X to X, where X is any non-empty set and G is a group. So here, as you can see, that uh, if you look at here, the group action here is, so the set is R3 and we're taking the GL3R as the group. So it's 3 plus 3 invertible dual matrices by, and the group action is via left multiplication. So how does it actually look like? So it's precisely like this. So if you take GL3R cross R3 to R3. So precisely what you're taking A, comma, let's say take a 3 tuple in R3 and you are mapping it to Ax bar. Alright, so I'm writing x bar as x1, comma x2, comma. Alright, so this is how GL3R plus R3 to R3 the group action is defined. Now we have been asked to find the number of orbits for this action. So what are practically orbits? The definition is, let's say if you have a group action G cross X to X, alright, so X belongs to X and orbit of X is precisely the set G dot X for all G belongs to G. So this is precisely the set of an orbit. Now there is this very good relation between orbit of X and if you take any other element Y in X, orbit of Y. All right. So the thing is that this is an exercise you can do it yourself, is that orbit of X is either completely equal to the orbit of Y if they have only a single common term, or they are totally disjoint. So orbit of X and orbit of Y, they are totally equal if they have a single element common. All right. So if there is a single element that is both in orbit of X and orbit of Y, then orbit of X is practically equals to orbit of Y. Okay. So uh, so now the second thing is that whenever we have orbit of X and orbit of Y, if there is no element, uh, if there is no element common, then we have quite trivially that orbit, both of the orbits are totally disjoint. So here, if you look at it, that whenever they're asking about number of orbits for this action, that means they're actually asking about number of distinct orbits. Okay, because as if you solve this exercise, you will know that orbit of X and orbit of Y are only considered two separate orbits only when they are disjoint. Okay, so now let's uh, take a dig to that problem. So that means what? That means if I take GL3R cross R3 to R3, since A is an invertible matrix, X bar goes to Ax bar. Since it is invertible, if you take this point in R3, so what is the orbit of this point? It's quite trivial. So let's call this as the 0 bar. So the orbit of 0 bar is practically 0. Okay, because if you take a dot 0, then it is 0. Now, no other non-zero x bar in R3 will fall into the orbit of 0 bar. Why? So now the first remark is no other x bar not equals to 0 will belong to the orbit of 0 bar. Why is that? Because if x is not equals to 0 and a x bar is equals to 0, this implies x bar equals to 0 because a is invertible. You can actually take it here as a inverse, then x bar becomes 0, but which violates our previous hypothesis that we are taking x bar not equals to 0. So one of the orbits of this group action will be the orbit of 0 bar. Okay, because that is a singleton orbit. So orbit of 0 bar is 0 itself. So let's just say 0 bar, since I'm taking to be 0, 0, 0, 0 bar. Another one is this. So if you take, so R3 is basically spanned by these three vectors, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. When I'm actually talking about the spanning of R3 over R. So these are the standard vectors, basis vectors. You might have also seen them in this form. So if you take AE1, what do you get? So how does AE1 looks like? So this is, let's say, your E, A11, A12, A13, A21, A22, A23, A31, A32, A33. So if you take this with 1, 0, 0, now look at the definition of orbit for all G in X. This will actually come into the picture right about now. So if you take the left multiplication, this, then what you have? Then you have this A11. So A11 then plus 0 plus 0. So then similarly A21, A31. So now if you take the orbit of E1, this will practically generate, the orbit of E1 is practically entire of R3 minus 0. The reason is that whatever the point you want to pick from R3 minus 0, you just put it in the first column of your A, and you put the rest of these two columns in your own accordance such that their determinant becomes non-zero. Their determinant becomes non-zero, thus making the matrix inverted. Okay, so if you take the E2, the orbit of E2 is exactly same. If you take E3, the orbit of E3 is exactly the same. Okay, so now since you have two orbits of E1 disjoint union orbit of 0 bar is your entire R3, you will only have two orbits for this group action, and that's precisely what this problem tells you to do. So this problem asks you to find the number of orbits for this action. So what did we understand? That at first, what are orbits of an element of the set? Secondly, the orbit of the set, two orbits of the set are either completely disjoint or they are completely equal. Thus, there is a set theoretic partition of the entire set as the disjoint union of orbits. And hence, in here, since we find the disjoint union of orbit, as the entire set we can think about. So then there are only two distinct orbit present in this group action. So those so thus the answer is. So that's it for today. So we will meet again with another problem from TIFR 2020 paper. Thank you for joining us. We will meet tomorrow.